All right, this is part 2. It's only 78, but I do want to talk about some of the stuff for the test. That's coming up later on, maybe next week, maybe the end of this week. I think it's the end of this week. Write the balance chemical reaction, that's what it should say, write the balance chemical reaction for the reaction that occurs in each of the following cases. So chlorine reacts with water. Okay, so let's take a look at this. First of all, chlorine is a gas, so we're going to start off with, it's part of Brinkelhoff. Don't forget about stuff like Brinkelhoff. We got a whole ton of things that we have to remember to do this stuff well. So chlorine gas then added to water like this, of course, will be liquid. So what happens on the other side? So here's what happens. Obviously the H2O breaks up. One of the H plus goes with the Cl to give us a very common hydrochloric acid. Of course, that's dissolved in water because water is present there. And then what happens on the other side is something that's not very typical, but we end up with, you will see it written like that. The other way you may see it written is HClO. So this is hydrogen hypochlorite, and this is one of those things that's like a disinfectant. And this is also dissolvable in water, like that. So let's take a look to see if we need to balance the equation. I have two Cl's on this side because of Brinkelhoff. I have one here and one here, so no, that's not a problem. Now I have two hydrogens on the left-hand side. I have one here and one here. So that's okay. I have one oxygen on the left-hand side and I have one on the right-hand side. So that just works out perfectly. Okay, so how about barium metal is heated in an atmosphere of hydrogen gas? Now here's what I know. What I know is that sometimes hydrogen can be a +1, sometimes it can be a -1. Actually, most of the time it's a +1, and then only sometimes when you have reactive alkaline or alkali metals, it can turn into a -1, and it has the same electron configuration as helium. So barium metal heated in an atmosphere of hydrogen. Don't forget about Brinkelhoff because he hasn't forgotten about you. And then on this side here, if I have hydrogen, of course we have barium and hydrogen. Barium has a +2, okay, and hydrogen will have a -1. So it looks like that 2 from Brinkelhoff doesn't go anywhere, but it actually does. It's not the same 2. It's not Brinkelhoff anymore because Brinkelhoff does not exist in compounds. But because of crisscross, we still get a 2 there for the H2. There's a good chance that this is going to be a solid, simply because most metals, when they combine with a non-metal, make a solid. So that's just something that usually happens. Let's keep going. Lithium reacts with sulfur. This couldn't be more of a straight. Okay, so in this case here, we typically have S8. Let's just go with regular sulfur here. This is going to be a synthesis reaction where we have one product on the right-hand side. We know lithium has a +1. We know sulfur develops, a -2 like that. So when I crisscross, I end up with Li2S1, but I don't have to write the ones. So I just simply get rid of that. And that means that over here on this side, for the solid for lithium, I'm going to have 2 lithiums on the left-hand side to balance with 2 on the right. So fluorine, F2, as a gas, reacts with magnesium metal. So that's Mg as a solid like that. Again, this is clearly a synthesis reaction. When I have 2 elements added together, I end up with magnesium as a +2 and F as a -1, which means the 2 comes down here. Again, this is one of those situations where Brinkelhoff looks like the 2 stays with it, but it does not. And this, most metals and non-metals produce a salt that is solid at room temperature. It doesn't look like I need to balance any equations with this one. So we're in good shape here. Okay, now let's take a quick look for the test. Know the trends for the properties of atomic radius, ionic radius, ionization energy, and electron affinity, because that's what we go over in Chapter 7. More specifically, why ionization energy has the pattern it has, and electron configurations for ions, specifically transition metals, because the S sublevel is taken first. Okay, that's how we make ions for the transition metals. Everything else, you take the electrons from the last term or you add to the last term of the electron configuration. You should know the chemical equation patterns for nonmetal oxides plus water always produce acids. Metal oxides plus water produce some type of basic compound. Hang on, I'm not done yet. There's more. Metal plus nonmetals, this is a synthesis reaction. We just simply make a compound out of them using the charges that they both develop. Alkali metals and hydrogen, that is a special case where hydrogen gets the -1 charge. Okay, so this is one of those cases where hydrogen actually develops a -1. So knowing the formulas for ionization energy and electron affinity. If you're not sure what I'm talking about, ionization energy would be like when we take magnesium in the gaseous form, and for ionization energy, this just goes to Mg with a +1 plus 1 electron, like that. Okay, and then it's going to be the opposite for electron affinity, where I have oxygen, and then it's +1 electron like this, and then it goes to oxygen with a -1. And of course, this is gas for both of these here also, like that. Okay, so this is ionization energy, like that, and this is electron affinity. Electron, there we go, affinity. Good. Okay, good luck.